Okay. I I'd said I'd talk about the Greek mathematics, so I wanted to do that. So to begin with, we're going to talk about what that all included in the beginning, and then we'll gradually include Egypt, which may not seem like it should, but it does. All right. So you can see that included much of what is Greece and Asia Minor, um, Crete, all of those, basically everything around the Aegean Sea and up into the Black Sea, Mediterranean, and Ionian. So this originates 6th century BC to about the 5th century AD. The word mathematics comes from the Greek word mathemia, mathema, meaning knowledge, subject of study, learning. So either knowledge of learning, knowledge of study, subject of study, subject of learning sort of idea. We might say subject of instruction. So these are some ways we may think of it. So we get our word from the Greek language. Uh, there had uh, they had a variety of ways of writing down numbers, which caused problems. So some Greeks used the system based on writing the first letter of the word for that number, usually uppercase. So for the number 10, deca, they would draw a um, uppercase delta to mean 10, not because 1 0 had not come yet. That wasn't a thing, right? So when they wanted to talk about 10 of something, they might denote it that way. But it isn't the only way. And this is part of the reason that the Greeks studied geometry more than anything else, is because this got confusing. Uh, Here you have the Greek alphabet, though some of these letters are not used any longer. Um, so most of these you guys should know, have seen at some point. Those with the asterisk are no longer in use. So the copa, the vowel, are no longer in use in the Greek language, though actually I don't think Sampi is used anymore either. Most of the rest of them look like they're used, but the problem became that they would use these in uh, capital, lowercase, and then not even by the first letter, right? So not always was it delta. This is lowercase, so these are all lowercase letters. Since the Greeks had a very clumsy way of writing down numbers, they didn't like computation, calculation, sort of stuff like that. So they didn't like algebra, though algebra wouldn't be invented, as the name goes, until later. They focused on geometry and used geometric methods to solve problems that currently you guys have probably used algebra to do. You guys use algebra to complete the square. They would have used geometry. Uh, they found it difficult to be consistent when writing down equations or number problems. So Greek mathematicians were very interested in proving that certain mathematical ideas were true, foundationally true. They spent a lot of time using geometry to prove that things were always true. Even though the Egyptians and Babylonians already knew that they were true, they'd used them, they understood them, they didn't really have any way to show they were true. And the Greeks really expounded upon this, and this is what built proof writing. Um, so some famous Greek mathematicians, Thales, Pythagoras, Anaxagoras, Democritus, Astraearchus, Eratosthenes, Aristotle, Hippocrates, Euclid, Archimedes, Apollonius, and Hypatia. Um, I'm going to briefly, well, I'm going to try to touch on a few of these, as many as I really can, though they might end up, this might be in 2 videos, so we'll see how this goes. The periods in Greek mathematics were kind of first, second, third. First is greatly influenced by Pythagoras and his teachings. So that means Thales had already been. These are fairly close to being in order. I'd have to really double check and see if they're not quite in order. The second would be Plato and his school, which would come into Euclid. And then we have the third, which is the Alexandria school flourishing in what we call Grecian Egypt. This extends to the influence of Greek mathematics to Sicily and Palestine. Um, so we'll start with the first one. So we're going to start with Thales before we get to Pythagoras, because I feel like maybe I'll break these into first period, second period, and third period. Uh, while Pythagoras had a big say, Thales of Miletus, well, he was the first of the Greek philosophers who took a scientific interest into mathematics, or the first we know of. He improved Egyptian mathematics. He knew of relations with numbers, what we might call number theory. In his work is the foundations of deductive geometry. He's credited with a few of the simplest propositions relating to plane figures. He created the first elements. That's Euclid will do later. Euclid will take Thales's elements, as he took most people's stuff, and compiled it. So he was really a editor. Euclid was. So if Thales had done this, he gave the idea of logical proof applied to geometry, and his great contributions lay in suggesting a geometry of lines and in making the subject abstract. Uh, Reportedly, now I don't know if this is all true, but being asked what was very difficult, he answered famously, to know thyself. Asked what was very easy, he answered, to give advice. And to ask who is God, he answered, that which has no beginning or no end. Yes, he was of the time, the old time, so not the Zeus, Hades, and Poseidonus type deities, though Poseidon is older than Zeus. Um, he was worshipped in pre-Hellenic Greece. Uh, so so were others, not all of the Greek deities that we know. But he was. And by general agreement, he was the first of the seven wise men. Um, a pupil of the Egyptians, though none of his actual writings survived that we know of. He was studying in Alexandria, Egypt, when he had a question: how high is the pyramid? None of the locals were able to help him, so he figured it out. He also reportedly used this knowledge to predict an eclipse of the sun on May 28th, 585 BC, accurately. Um, the five basic propositions of plane geometry are attributed to him, uh, and they go something like this. So, a circle is bisected by any diameter. So, any diameter will bisect a circle, creating two half circles. The base angles of an isosceles triangle are equal. Well, if you know your geometry, that should feel totally natural. That is a proposition that Thales proved to be true. The angles between two intersecting lines, intersecting straight lines, are equal. So the angles between two intersecting straight lines are equal. In this case, this would be something like this angle. It's a straight line, and this angle, it's a straight line. So this line is a straight line. So this angle and this angle must be equal, and this angle and this angle must be equal, um, which is very true. What else? So proposition two angles are congruent, or two triangles are congruent if they have two angles and the included side equal. So that means the side between the two angles must be equal for that to be true. What else? An angle in a semicircle is a right angle. So this one, This one is a pretty neat proof. I like that one, so let's maybe talk about that one a little bit. So the proof would go something like this. An angle in a semicircle is a right angle. So you'll see that I have a semicircle from C to D. That is a diameter, so it bisects from that first proposition. It bisects my circle, and it means that this circle is half of this circle. Okay, and then from that, I've created these other triangles. I'm using A as the center of my circle. So AC is equal to AD is equal to AE. They're all radiuses of the same circle, so they must be equal. And then I've labeled alpha, beta, and gamma and gamma. So AC is equal to AE. Therefore, it is a isosceles triangle, right? That's the property of isosceles triangles. The legs are equal to each other, or the two sides are equal to each other, which this is. And that tells me that these interior angles, again from previously, must be the same. I've labeled them gamma. It also means that AE and AD is an isosceles triangle, and uh, delta and delta must be equal to each other because the sides are. So I have those properties. I also have the property that alpha plus beta must equal 180, right? Alpha plus beta must equal 180. So 2 of gamma and alpha must equal 180, and 2 of delta plus beta must equal 180. So putting them all together, 2 alpha or delta and gamma, 2 times those two, I'm combining them, plus alpha plus beta must equal 360. I'm basically adding these two together. Uh, I know that alpha and beta must equal 180, so I could take that down by 180. I could divide it by 2, and that would give me 180 divided by 2, which would be 90. So delta plus gamma must equal 90. That means that this angle must be a right angle. I feel like it's a pretty straightforward proof. This isn't really that crazy. Do you need a picture for this proof? No. Would you need more words to define where everything is? Absolutely. This isn't a formal proof without this picture. It could be a formal proof without the picture if we use more words to define alpha and beta and gamma and delta, then yes, we could. But it is definitely a good skeleton of a proof. You'll find that proof writing, I think, is a very formal type thing. So next we're going to have Pythagoras. Some called him the first pure mathematician. He worked with abstract geometric objects and numbers, gathered his school as a sort of mathematician secret brotherhood. He would talk through a curtain to his people. He took stuff from the Egyptians, the idea of a right triangle, and the Pythagorean theorem, and then proved that it would be true. So the proof comes from him. In a right triangle, the sum of the squares of the two right angle sides, the two right angle sides will always be the same as the square of the hypotenuse. Only a right triangle can have a hypotenuse because hypotenuse is the side opposite the right triangle. And I know he did this. We know he did this, but we also know he's not the only one to understand this. The Greeks, like I had mentioned, or the Egyptians had used this to partition land. This was a way they used it. They had ropes tied at equal intervals for 3, 4, 5 triangles, which are right triangles. And so they would tie links of rope into knots at 3, 4, and 5 to show that they had measured correctly. That unit, whatever that unit is, was equal for all of the ropes. And they could use these to partition the land after the flooding in Egypt. So this was a common use. It was a regular practice. Um, but that isn't the only thing. The only property that Pythagoras did, though this is probably his most famous because all high school kids learn this and even middle schoolers learn this. So, but he also figured out this property. These numbers are clearly the squares of the integers 1, 4, 9, and 16. So 1 squared is 1. 3 squared or 2 squared is, if we look down here and we say, okay, 1, 2, 3, 4, 5, 6, but 1 squared is going to be 1. 3 or 2 squared is going to be 1, 2, 3, 4. 1 and 3. 3 squared is going to be 1, 2, 3, 1, 2, 3. So 9, which is really 1 plus 3 plus 5, which is 9. And then as we do the fourth one, so we would go down and over. So what these are doing is making square numbers. So these are the square numbers. 1, 2, 3, 4, and 4 is 16, which is the same as 7 plus 5 plus 3 plus 1, which is how many are in each one of these little curved columns or turned columns. 5, as you see, we'll go down, they'll have 9, so this would be 25. And if I sum up 9 and 1 and 7 and 3 and 5, I would have 25. This 6 is going to have 11 in its space, which is going to be 36. So if we add the consecutive odd numbers, so 1, 3, 5, 7, 9, 11, these are consecutive odd numbers, we're actually getting the squares of these numbers. So that's pretty neat. Well, I think so. What else? So the Pythagorean philosophy, transmigration of souls, purification rites, developed rules for living believed would enable their souls to achieve a higher rank among the gods. Theory that numbers constitute the true nature of things, including music. Now, this is interesting. Synthesia is a condition that most children have at birth and gradually happens as we age, that our nerve endings separate. But some people have synthesia, where the nerves don't actually separate, or some of the nerves don't separate. And it's very possible that Pythagoras had this condition because he had this connection of how numbers were everywhere, and that proper use of numbers would create the perfect musical sound symphony. So the Pythagoreans believed when someone was in doubt as to what he should say, he should always remain silent. Well, that's a good rule. It was better to learn none of the truth about mathematics, God, and the universe at all than to learn a little without trying to learn all. So they felt like you couldn't just touch it and not want to learn more. Pythagoreans' inner circle were called mathematikoi, or mathematicians, and the outer circle were kousmatikois, which are listeners. The listeners were the exoteric disciples who listened to the lectures that Pythagoras gave out loud from behind a veil. And the Pythagorean theory of numbers still debated among scholars. Pythagoras believed in a harmony of the spheres, that the planets and stars moved according to mathematical equations which corresponded to musical notes and thus produced a symphony. He also had the Pythagoras of Pythagoras. That would be something like this. Now, do we know that this? We know most of what was said. We don't know exactly every particular prayer type thing. So bless us, divine number, thou who generated gods and men, O holy, holy Tetrax. Though that containeth the root and the source of the eternal flowing creation. For the divine number begins with the profound, pure unity until it comes to the holy four. Then it begets the mother of all, the all-encompassing, all-bounding, the firstborn, the never swerving, the never tiring, holy ten, the key holder of all. So interestingly enough, he connects the number 10 to being very important. And he thinks of it as a 1 to 4, like triangular numbers, which is okay, interesting. But it is an interesting, I think it is interesting that at this time, we didn't have a base 10 number system, right? We had 12, which was the most common, or 60, but we didn't have a base 10. Base 10 really starts to happen with Pythagoras. And then the Hindu Arabic numerals that you guys use comes about. So it's pretty crazy that this was going on. What does this connection to music mean? Well, the diatonic ratio of highest to lowest pitch is 2 to 1, produce the interval of an octave. An octave, in turn, divided into into a fifth and fourth with ratios 3/2 and 4/3, up a fifth or up a fourth, up an octave. Fifth divided into 3 whole tones, each corresponding to the ratio of 9/8, and a remainder with a ratio of 256 over 243. Fourth into 2 whole tones with same remainder. Harmony, combination of ratios of numbers. The whole cosmos and individual do not arise by a chance combination and must be fitted together in a pleasing or harmonic way, in accordance with the number for an order to arise. Discovery that music was based on proportional intervals of numbers 1 to 4. He believed the number system and the universe based on their sum was 10. Swore by the tetrarchs rather than by the gods. Odd numbers were considered masculine and even were considered feminine. I will mention, because of course we should, there was a mathematician, a person who had said, well, what happens if we look at triangles, right triangles with a unit of 1, if each leg was 1? And this mathematician was Hippasos, and that discovered the square root of 2. Problem is they didn't have square roots. Numbers needed to be whole numbers. And so his claim that using what Pythagoras had already claimed would give us this square root of 2, this irrational number, caused a problem with some of the Pythagoreans. So rumor says Pythagoras ordered him removed, and he was executed. Yeah, they killed him because they weren't ready for irrational numbers. His system hints at a heliocentric theory, which the Babylonians, the Sumerians, the Egyptians kind of all believed in. So this is normal, though it will come back later that society as a whole stops believing in it. All right, so this is a good place to end, and then this is the end of the first period. We'll go on and do the second period next.